Back everyone to the school. Today we have it's my pleasure to introduce Professor Sandro Scandolo, pioneer contributor of condensed matter physics with his studies in material science and atomistic simulation. Sandro is a long-term member of the ICTP, initially the position of research scientist, then became the head of the condensed matter section, and now acting as a research director of the center. Sandro today will speak about ab initio molecular dynamics with, and actually we have the opportunity to test this innovative lecturing methodology where Sandro is hidden somewhere at the ICTP. Nobody, apparently there is a legend ongoing here in the center that nobody knows where he effectively is. And actually would be the game of today will be to find him out where he's hiding in the center. But meanwhile, we'll enjoy his talk. And so, Sandro, stage is yours. Welcome, also welcome to the school from the organizer.
Thank you, Ivan. Thank you, everybody, for connecting so early in the morning. It's really my pleasure to be here, actually, to be testing this system, which I mean, those of you who know my lectures in solid-state physics might know that I like using chalks and blackboards. So this is actually a new setup that was created by our scientific the Fab Lab, the Sci-Fab Lab here. It's still rudimentary, but I'm actually testing with this lecture. So it's you can consider it also as a test of the system, and I hope everything works today. So the lecture today will be about ab initio molecular dynamics. You'll have some tutorials later on, hands-on. But since I guess most of you come from the background of electronic structure calculations, the idea is that I will start with some introductory concepts in the field of molecular dynamics. Okay, so my lecture will be structured in more or less two parts. First, I will give you some brief introduction to the basic concepts of molecular dynamics, and then I will move on to the concept of potential. And this is where the ab initio part comes in. And I will also try to show you some simple methods to do ab initio molecular dynamics, among which the famous Carr and Parinello method. I mean, Roberto Carr and Michele Parinello developed this method actually here in Trieste almost 40 years ago, 35 years ago, but it's still a method that is used in practice for ab initio molecular dynamics. Okay, so let me start. It's some very basic concept. So what is molecular dynamics, first of all? Molecular dynamics essentially consists in simulating the dynamics of molecules, or in fact, the name molecular dynamics is an historical, in some sense, mistake, because we are not just dealing with molecules, we're dealing with atoms, we're dealing with any particles, as a matter of fact, as long as it moves with Newton's equations. So it should be called actually atomic dynamics more than molecular dynamics. So you have a bunch of atoms that you want to study the dynamics of. You have some forces acting on the atoms. Let me introduce some notations here. I will consistently use capital letters for ions, atoms, and small letters for electrons, because electrons will come into play later on, of course, because we're doing ab initio molecular dynamics. For the time being, it's just classical, okay? I'm just dealing with the classical system of particles. Each particle will have a force attached to it, and the idea is that we want to essentially solve Newton's dynamics for these particles, right? So mass times acceleration, this is the second derivative, and this is equal to the force acting on that particular particle. Okay, so we want to evolve, we want to solve this problem. And in solving this problem, let me right away mention that there are two aspects which are quite complementary. One is the aspect of how we're solving this as a second order differential equation, because this is what it is in practice, right? It's a second order differential equation in time. And there is another aspect, which is in fact probably the most interesting one in some sense for us, for our community, for the ab initio community, which is how I calculate the forces acting on the particle. And this is where, of course, the ab initio theory comes into play. Now, when you set up a simulations, of course, you have to define the atoms that you have in your system. For example, this could be a 4-atom molecule, and you want to study the dynamics of this for a certain amount of time. But in most cases, you do ab initio molecular dynamics to study behavior of bulky systems, right? Liquids or collections of molecules, water, for example, or amorphous systems. So you're actually, your goal is to study systems that are actually, macroscopic in size. And I don't need to explain you this concept, right? You're already familiar with the concept of a simulation cell, where you, of course, you restrict your system into a given box. And you're also familiar with the concept of periodic boundary conditions. But in the concept of periodic boundary conditions in molecular dynamics is a bit more, it's a bit less obvious, because you're dealing with systems that move, and you're dealing with systems at finite temperature. You're dealing with liquids, right? So there are no periodic there is no periodicity in a liquid. So what you actually do in practice, if you have say a macroscopic system of particles now, let's imagine that this is 10 to the 23rd particles, which is roughly the size of a macroscopic system. You don't want to study 10 to the 23rd particles in the computer. So you need to, and they're all different in some sense, right? There's no periodicity in principle if this is a liquid. So what do you do in practice? Well, in practice, what you do is essentially that you select a subcomponent of your system, and you're simulating only that small component based on the availability of your computational resources. It can be 100 atoms, it can be 1,000, it can be 1,000,000 atoms, depending on the size of your computer, the one that you have available. So the first question that you ask yourself if you do molecular dynamics is, how do I truncate my system? Right? Which kind of boundary conditions I'm going to apply to my system. Now, you're familiar, as I said, with periodic boundary conditions, but this is not obvious at all, because periodic boundary conditions in principle introduce a spurious periodicity in your calculations, right? If you're studying a liquid with periodic boundary conditions, you're not studying a liquid, you're studying something which is periodically, in fact, you're studying a crystal, if you wish, because even if your simulation box contains 100, 1,000 atoms, these 1,000 atoms repeat periodically, right? So there are some artifacts that are introduced by the introduction of periodic boundary conditions. In fact, in the early days of molecular dynamics, people were not actually using periodic boundary conditions. They were using open boundary conditions. They were putting the atoms in selecting, say, a chunk of the system, and then just put vacuum outside, and just calculating the forces between the particles inside this cluster. Let's call it cluster. Now, there was a debate, especially historically, whether open boundary conditions were better or worse than periodic boundary conditions. Periodic boundary conditions, from the computational point of view, are slightly more complicated, because you have to compute forces coming from, infinitely many particles, while with open boundary conditions, you're only looking at forces coming from a finite number of atoms. So from a computational point of view, open boundary conditions are slightly easier. Of course, open boundary conditions means that you're exposing a number of atoms to a surface, to the vacuum, right? Which is clearly unphysical if your goal is to study a bulk system. And this is actually quite serious, more serious than perhaps you may imagine. Just give you an example. Suppose you take 1,000 particles, right? And you put them in a cube with open boundary conditions, right? Suppose that the system is simple cubic, all right? So you have 1,000 particles, you have a cube, and the cube is of size, say, 10 times 10 times 10, okay? And you're doing this with open boundary conditions. Now, can you guess the number of particles that are at the surface of this big cube? Well, I'm sure you're now trying to calculate it, but you have 6 faces, and each face is about 100 particles. So you immediately realize that more than half of the particles that are in a cube of size 10, so 1,000 particles, are actually at the surface of this cube, right? You thought that 1,000 was a big number, but you realize that you try to take a cube made of 1,000 particles, more than half are actually at the surface of this cube. And you don't want to, clearly, the particles that are at the surface are not going to evolve dynamically like a particle in the bulk, because they're actually, they're at the surface. So there is actually half of the forces acting on those particles. So you immediately see that open boundary conditions really need to go to very big simulation boxes if you want to achieve something that looks like a bulk state. So something where the vast majority of the particles in your system is actually in a bulk state. Completely surrounded by other particles. So the concept of periodic boundary conditions been, in fact, taken over as the main way to do boundary conditions in molecular dynamics. Now, there are even more exotic choices. People have experimented something like twisted boundary conditions. These are actually quite common in the field of when you simulate wave functions, because you're also introducing some k-point sampling. But that's a different story. So we discussed periodic boundary conditions. We sort of concluded that what we want to do is to study essentially systems inside some simulation box, which is representative of a large amount of particles. We put our particles inside our simulation box, and we now want to evolve them according to Newton's equations, and we use periodic boundary conditions. That is, if a particle gets to the surface of this box, it will automatically re-enter from the other side of the box. We use periodic boundary conditions, okay? So as a matter of fact, what you're studying is not just, completely disordered system. You're studying a liquid, but you're studying a system which is periodically repeated in space. And what you have to make sure is that the size of your simulation box is not introducing some spurious unphysical effects in the results of your simulation. So you normally try to do bigger and bigger sizes to try and see whether there is anything in your calculations that depends on the size, which is of course something you have to fix, of course, in your simulations. Okay, so let me now go back to the solution of the second order equation, which is one of the first steps you have to consider. How am I going to solve this second order differential equation? So in order to do that, let me actually share the screen, because it's probably faster if I do that. Let me go straight to the to this one here. Okay, I hope you can see this. Yes, I'm sharing the screen. So as you can see, meanwhile I will erase this blackboard. As you can see, I mean, the goal is to essentially evolve the position of a given particle, which is R capital I, with time. And the way you do that is by discretizing time, sorry. You discretize your time in small steps, and I'll come back to the choice of the time step in a moment. And essentially, what you want to do is to guess, try to come up with the best guess of what will be the position at time t plus delta t once you know the properties of your system at time t. For example, position and velocity, and of course the force, because you're calculating the force, right? So based on the force, you want to guess what will be the coordinate of the position, atom I, for example, in this particular example, at time t plus delta t, once you know the position and velocity at time t, right? And this is going to be an iterative procedure. You start with the given positions and velocities, and then you evolve iteratively this process for as long as you want, essentially, as long as your computer resources allow you. Now, there are a number of subtleties in doing this. The most important concept that you have to consider is that you want to minimize that particular the error that you're making when you truncate this sum, right? Because you know the position, you know the velocity, you know the force, but you don't know what comes next, what comes at the third order in delta t, right? This is the third derivative of the position with respect to time. So if you truncate your estimate just after the force, you're going to make an error which is of order delta t cube. So you want to try and minimize as much as possible that error. Okay. So there are a number of tricks, and there are several algorithms that try to improve this. But let me just give you a flavor of how these algorithms work with a given example. This is called the Verlet algorithm. The Verlet algorithm starts from the consideration that if you actually do the same exercise with minus delta t, and I'll show you in a moment why it's interesting to look at minus delta t. What you'll find, of course, is something where the terms that change sign are the velocity term, the ones, of course, which are odd in delta t, and of course, the term in delta t cube, whatever it is, right? You don't know what it is, but you certainly know that this term is going to change sign when you reverse the delta t. Of course, the term in delta t fourth will have the same sign and will have the same sign. Now, if you sum these two expressions, you just sum, the left-hand side and the right-hand side, and what you see is that two things. First, the velocity disappears, right? You don't need any longer to know what the velocity is. You just need the positions. Of course, you need to know also the position at time t minus delta t. In other words, your estimate of the position at time t plus delta t depends on the position at time t, position at times minus delta t, the force at time t. And then the interesting thing is that whatever remains, the residual of this calculation is now one order higher in delta t. It's now of order delta t to the fourth. So essentially, you've been able to reduce the error that you are making. Okay, so this is a very popular, it's probably the most popular algorithm in molecular dynamics, because it only requires the knowledge of the positions at the previous step and the two steps before the one you're calculating. Okay, and of course the force, because the force is what guides you in your in the definition of the trajectory. And the error you're making is to order delta t to the fourth. Now you can easily imagine that you can make this algorithm following similar procedures, similar derivation. You can actually, by including memory of the system at time t minus 2 delta t or t minus 3 delta t, you can make that error delta t fourth even smaller by going to delta t to the fifth, delta t to the sixth, and so on and so forth. So it can be systematically improved, following essentially the same derivation as the one that I've just shown you here for the first order, essentially. So it is. I mean, you have in principle the possibility to make it systematically better if you want. But Verlet algorithm is already an extremely stable algorithm. Another reason why Verlet algorithm is quite popular, especially in molecular dynamics, is that molecular dynamics simulations are never too long in time, because ab initio molecular dynamics is much heavier, computationally speaking, with respect to standard molecular dynamics, right? So with standard molecular dynamics, you can run systems for, even for microseconds. I mean, there have been simulations that have been running for milliseconds. With ab initio molecular dynamics, instead, you rarely go above, say, 1 nanosecond. Okay, the typical ab initio simulations is between 1 picosecond and 1 nanosecond, right? So it's actually quite short in time, and errors that come from the integration of the equations of motions are less serious than errors that you do in the case of classical molecular dynamics, where you evolve your trajectory for a much longer time. Now, let me actually say something about delta t now. How do we actually choose delta t? Okay, so let me actually go back to my screen here. And so I have my time here, my position here as a function of time, and I'm discretizing my trajectory, my time, right? The distance is delta t, and I'm evolving my trajectory in this way. Okay, and so on and so forth, right? So I have a discrete set of points which describe more or less the trajectory of my particle, right? And these are discrete points, of course. So let me highlight the fact that what I have is not, of course, a continuous set of points, but it's a set of points that are defined only where the delta t, every delta t, right? So this is what I call my trajectory. Now, the question is now, how do I choose delta t? Of course, I would like to make, there are two contrasting arguments that I have to take into consideration when I choose delta t, right? Based on what we just discussed, I want to make delta t as small as possible, because the smaller is delta t, the better will be my integration, the more precise will be my estimate of the position at time t plus delta t, right? I'm making this error, which I now discussed, which is of order delta t to the fourth in the case of the Verlet algorithm. I'm making it as small as possible. So on one hand, I would like to make delta t as small as possible, tiny. On the other hand, there are some obvious considerations coming from the fact that I want to simulate a system for a given amount of time, and the given amount of time is determined by the physics of my problem, right? I want to simulate, I don't know, I mean, the vibrations of a molecule. I need to be able to simulate my system for at least several periods of vibration of my molecule, right? So the physical problem I'm interested in will set the actual time scale I need to consider. So if I make delta t too small, the total number of steps that I have to, iterate my trajectory will be, of course, inversely proportional to delta t. So if delta t is too small, right, obviously, the total trajectory, let me call it t, the total, length of a trajectory will be, of course, a number of steps times delta t. So if delta t is too small, the number of steps will be too large, and so the calculation will be too long. It will take too long, right? So I have these two conflicting criteria that I have to somehow try to accommodate. Well, it turns out that at least with the Verlet algorithm, as a rule of thumb, if you consider the typical fluctuation of your system, okay, which can be here, for example, represented by this roughly, right? Let me call it tau. This is a sort of characteristic time of my system. For example, if I have an oscillator, it will be the period of the system. This is more or less the time that describes the oscillations, the average oscillations of my system. Well, as a rule of thumb, in order to be able to integrate this properly, certainly my delta t must be much smaller than tau, obviously, right? Otherwise, I won't be able to describe a fluctuation. But as a rule of thumb, it turns out that delta t can be, if I want, of the order of, I can make it something of the order of 30 times smaller. It can be 25, it can be 40, depending on how accurate I want this oscillation to be described. But the Verlet algorithm in particular is quite stable if you choose a delta t, which is only 1/20th or 1/30th of the actual period of oscillation of your system. Okay, so in practice, your system will be a complicated system and may have different time scales. Take water, for example, right? Water, liquid water, there are several time scales. There is a time scale of diffusion, which is normally a fraction of picoseconds. And then there is a time scale, the fastest one is the time scale of the vibrations of the OH bond, for example. This is actually extremely fast. So there are different time scales. So how do you choose actually your delta t in a molecular dynamics simulation? Well, you need to integrate all your degrees of freedom. So if you want to do that, you need to be able with your delta t to describe the fastest ones. Once you describe the fastest ones, you of course be able to describe also the slowest one with the Verlet algorithm. So as a matter of fact, your delta t must be a fraction of the order of 20, 30 times smaller than the fastest oscillation of your characteristic time of your system, okay? You have to pick the fastest oscillation time. In the case of a water molecule, for example, that would be the stretching of the OH bond. And then that defines your minimal time scale that you have to be able to reproduce in terms of oscillations, and then your delta t will be correspondingly set, right? And in some sense, those of you who might be familiar with the simulation of water, you might now understand why a number of water models assume that the molecule is a rigid object. 90% of the molecular models for water using molecular dynamics assume that the water molecules is a rigid object, right? Of course, by doing that, you're introducing a lot of approximations because you're not looking at the dynamics of the water molecules. But in practice, you immediately see that this gives you a huge advantage in terms of delta t, because you can actually now, you can forget about the fast oscillations of the stretching of the bonds, and you can only integrate, you only need to integrate the dynamics of the relative motion of the water molecules and rotations, which is much slower. And therefore, this allows you to use a delta t, which is much longer than the one you would have to use if you wanted to integrate integrate the short one. Okay, good. So let me now move on, and let me again share the screen and show you. Let me see. Okay, right. So this is a standard protocol of a molecular dynamics simulation. You first initialize your atomic positions. You need to give some initial positions and velocities, because you remember, I mean, in the algorithm, you need to know, well, either the velocities, or you have to give the positions at time t and time 0 and time delta t, which is sort of equivalent to given velocities. That initializes your simulation, and then you start running your simulation. Now, of course, if you want to study your system at a given temperature, you have to choose atomic positions and velocities that are, you know, as much as possible close to what you think is going to be thermal equilibrium at in your system, right? For example, it doesn't make sense to start, if you want to study a solid, a crystal, at I don't know, room temperature. It doesn't make sense to start from the crystalline positions, because this is not a good, you know, a representation of your system at finite temperature. At finite temperature, the atoms will be already displaced from their position. Similarly, the initial velocities, you can actually choose them. This is simple. This is simpler. I mean, choosing velocities, you can actually do it quite in a straightforward way, because you can just sample the Boltzmann distribution. So you can choose initial velocities that are somehow chosen to represent, to describe the Boltzmann distribution. Okay, so you start with your simulation, you start calculating your forces, and you start evolving your trajectory using Verlet's algorithm. And how much you need to wait? Well, if you are interested in reaching thermal equilibrium, there are, I mean, different goals that you can give yourself. I mean, if you're only interested in looking at vibrational frequencies of a molecule, for example, you're not interested in reaching thermal equilibrium. You just want to know, you know, the period of the oscillation of the molecule. But in most cases, you're interested normally in study systems at thermal equilibrium. So what you do is you let your system evolve until the system reaches some sort of thermal equilibrium. And certainly you want the system to lose memory of what was the initial configuration, because that initial configuration was chosen, you know, out of a guess. So you don't want that guess to affect the final result of your calculation. Okay, and then once you reach the equilibrium, you start, you know, accumulating averages of the observables you're interested in. Here, this is just the generic you know, definition of an observable. Let me give you one example. I mean, it could be the temperature, for example, the instantaneous temperature of your system. Temperature, in the specific case of this, you know, equation, A for temperature would be just p squared, the sum of all p squared, the velocity squared. But you can also calculate other averages if you want, and you can average it over the length of the simulation. Now, it's interesting at this point to make somehow a connection with statistical mechanics. I think this is an interesting consideration that perhaps there's no time to go into any detail now, but you're of course familiar that in the realm of statistical physics, averages are calculated in a rather different way, right? They're calculated as averages over the over the Boltzmann factor, right? Using standard techniques in statistical physics. So the assumption here is that the molecular, in fact, it's rather an assumption on the side of statistical mechanics. We know that the real system behaves like a Newton, follows Newton dynamics. But if you average your system over long times, the assumption is that this averaging will eventually be closer and closer to the averaging, the perfect averaging that you would achieve if you were doing perfect statistical sampling of your observable. Okay, so there is an hypothesis here, and there is those of you who are interested, there is also the assumption, the ergodic hypothesis hidden behind this equation between the two averages, because in writing the right-hand side, you're assuming that the system is free to sample all possible configurations that are available in phase space. In molecular dynamics, you never know, because you might be stuck in some local minima, for example, and you don't know whether another minimum exists as long as you're exploring with your dynamics only a certain minimum. Okay, I mean, this is not, I don't want to enter into it. There's of course a huge, literature on this. And I just wanted to give you some hints that this is sometimes a problematic aspect that you need to consider. So let me again show you in practice what happens. This is a simulation in which the goal is to simulate your system at room temperature, right? 293 Kelvin. So you start from different initial conditions. You try to guess, the initial conditions in such a way that your system will reach room temperature. But as you can see here, your initial guess is never perfect, right? It's a guess. So it is a fact that if you evolve molecular dynamics simply using Newton's equations, you're actually, this is now the instantaneous temperature that you calculate in your system. So let me just show it here. 1 second. Oops. Sorry. Time here to erase the blackboard. Okay, so in this particular case, what I'm calculating was the instantaneous temperature, which is essentially, now I have to remember the factors now. Well, there's certainly a sum over the particles of their kinetic energies, VI squared, right? So this is, well, I know this. I mean, the equipartition theorem, this is 3 over 2 n number of particles kBT, right? This is from equipartition theory. So the instantaneous temperature is now 1 over 2 over 3 number of particles kB. Okay. So if I calculate my instantaneous velocities here, and I compute this object, I divide by the number of particles and by kb, what I get is, well, I can define it this way, right? And notice this value depends on the velocities at any given time. So it's not a constant. It will actually vary in time. So let me go back now to these curves. These are actually curves that show you the instantaneous temperature along different runs, where essentially the difference was only the choice of the initial conditions. By the way, the choice of the velocities, as I said, is typically straightforward. You just sample the Boltzmann distribution at the temperature you want. So here it was 293. But in terms of positions, there's no way you can guess with exactly what will be the positions that sample the e to the minus beta v, the potential part. So you can only guess it, right? You can try to displace the particles a little bit and try to guess what will be the equilibrium values. A value of the displacements, which gives you the final temperature that you want. So you can see different choices of the initial guess lead actually to different values of the average temperature that the system reaches after quite some time, after equilibration. Okay, what you see here is also the fact that it takes time, normally of the order of 10,000 steps in this particular case, to reach what we can call equilibrium. At the beginning, everything will fluctuate because you started from a configuration which is not representative, which is not exactly representative of your statistical system at the given temperature. But after a while, the system will reach a state which is stable in some sense, where the averages can be calculated and the temperatures will be different. So this, of course, raises an important question, and this is, how can I actually simulate my system? Stop sharing here. How can I actually simulate my system at a given temperature? Right? You don't want to, do trial and errors. You want to simulate your system at room temperature. You don't want to, start with different guesses and then choose the one that gets closer to room temperature. Now comes the concept of simulating, doing molecular dynamics in different ensembles. Okay, so far I've essentially described molecular dynamics as a solution of Newton's equations. Now, Newton's equations, as you know, conserve the energy, right? The total energy of the system, that is kinetic energy plus, sorry, I'm using here total energy in a different meaning than in standard ab initio. Here, for me, total energy is the sum of the kinetic energy and the potential energy, right? In classical mechanics, if you evolve a system with Newton's equations, that energy is conserved, right? So we call these simulations, we call them microcanonical simulations, okay? So a simulation where energy is conserved, we call them microcanonical. Microcanonical. Okay, but sometimes what you want is simulation in which instead temperature is, I wouldn't say conserved, but I would say where it's the simulation reaches samples the canonical ensemble. Okay, I'm using here conserved, but it's not actually conserved because temperature will always. What I mean by that is a simulation in which I'm actually sampling the canonical ensemble at a given t that I can give at the beginning of the simulation, okay, at given t. This is not what we did a minute ago. A minute ago we did this, and we didn't know what the final temperature was. Now we want to do something else. We want to do a simulation, a canonical simulation at the target temperature that I impose to my system. Now, the trick to do that, and there are several tricks to do that. I'm just showing one because there are plenty of tricks to do molecular dynamics in the canonical ensemble. Let me just, describe what very qualitative terms how one goes about doing that. Right? You have your equation, which is the Newton's equation. Well, what you do is, in addition to your force, you add a friction term, right? A friction term is proportional to the velocity of your particle, right? And you modulate your friction in such a way that you reach exactly the same temperature you want, okay? So if your instantaneous temperature is above the target temperature, then you switch on the friction. Vice versa, if the temperature is below the target temperature, you actually change the sign to this friction and you accelerate your particles, right? You make gamma negative, and in this way, you actually accelerate your particles. You give an acceleration which is proportional to the velocity. So the trick here is, how can I modulate gamma in such a way that I reach a target temperature? Now, it turns out, and there's of course plenty of literature on this, and I can point you to the correct literature, is that the best way to do it is to actually do it in a slightly different ways than I described it here, and by saying that this actual gamma is the derivative of an object which evolves with this equation, essentially, where this is the difference between the instantaneous temperature and the target temperature. Okay? So now this is a slight variant of what I described before, but it still goes in the right direction, because if the instantaneous temperature is above the target temperature, I want gamma to be positive, to increase, right? Because I want the friction to start acting on my velocities, on my acceleration here. Vice versa, if the instantaneous temperature is below the target temperature, this becomes negative, and gamma gets reduced until it becomes negative and accelerates the particles, right? Now, it turns out that this mathematical framework is an extremely nice mathematical framework that you can show. It samples exactly the canonical distribution at a given temperature. And there is actually a nice mathematical proof that was derived by Nozé in the, I believe in the 70s, probably early 80s or late 70s. Okay, so this sort of algorithm actually goes under the name of the Nozé thermostats. So these are called thermostats in general because these are algorithms that allow you to sample the canonical distribution while you're doing molecular dynamics. Now, you have to be careful. If you do this, you'll be sampling the canonical distribution, but you'll be completely losing the real dynamics of your system, because you're introducing a term which is totally fictitious. It's nothing to do with the physics of your system. It's something that you're introducing to make your calculation sampling the canonical ensemble, okay? So if you do this, you'll be able to reach the canonical ensemble, but you forget about extracting dynamical information from your trajectories, right? So the frequency will be completely, they will be slightly different with respect to the real frequencies of your system. The diffusion coefficients will not be the real ones, okay? So in practice, what you do is you first start with this framework, with the canonical simulation, and then at some point you just switch off your thermostat and you let the system evolve freely. Hopefully the temperature in the microcanonical ensemble will be very close to the temperature. If the system was equilibrated, was at equilibrium, will be very, very, very close to the temperature you fixed in the simulation done with the canonical ensemble. Okay. So this is thermostats, and of course there are many different applications of this concept of thermostats. You can actually extend this not only to temperature, but you can extend it also to pressure, for example. You can microcanonical simulations are, the cell is fixed, everything is fixed, energy is conserved. There's no chance the system can, say, change the volume or change, or change the pressure. Well, actually the pressure will fluctuate, but the volume will essentially remain fixed. So there are techniques which essentially are all inspired by this concept of thermostats that you can apply to sample other thermodynamical ensembles. For example, the constant pressure ensemble. I'll show you an example right now of what. Let me share the screen again. Okay, let me see. Yes, this one, for example. This is something that was introduced by Michele Parinello and Isra Mann in the early 80s. And it's you see the similarity between what I showed before at the blackboard, the temperature, and here now the pressure. So instead of considering now a friction part, you consider the cell as varying in time. So H here is the vector, it's actually the matrix that defines the three vectors that define the simulation box. And you're giving now the freedom to the simulation cell to vary in shape, you see, and with a dynamics, and what you see at the bottom is the dynamics of the cell now, of the H matrix, which is driven by the unbalance between the instantaneously calculated stress tensor, okay, the equivalent of the instantaneous temperature in constant temperature simulations, and the pressure, the target pressure that you want to achieve. In other words, if the system will reach an equilibrium only when, and actually the shape of the cell will reach equilibrium only when the internal stress is equal to the target pressure. Okay, so this is a mechanism to drive your simulation towards the target values of the the thermodynamic variables you want to fix, which is temperature in the previous case, and it is pressure in this particular case. Okay. Let me stop sharing here. Okay, now I just wanted to give you one example of quantities that you may wish to calculate out of a molecular dynamic simulation. A temperature is one, of course, and I just showed it before. You may wish to compute the instantaneous temperature and to monitor the instantaneous temperature while you're evolving your trajectory with time. And this is actually a very good way to determine whether you've reached equilibrium, because the fluctuations of the temperature tend to remain say constant around the given value, which is the equilibrium value of the temperature. By the way, you will never get rid of fluctuations in your simulations, right? Even the instantaneous temperature will always vary in time. What you need to make sure is that its average remains constant. This is equilibrium. But the instantaneous value of the temperature will, of course, always fluctuate. And the fluctuations will actually be, it can be shown, will be proportional to the inverse square root of the number of particles of your system. Okay, so the oscillations of the instantaneous temperature. This is actually quite clear if you think about a single particle, right? Think about just a single harmonic oscillator. In a single harmonic oscillator, there's essentially only one type of dynamics, this one, right? And the kinetic energy, the average kinetic energy of your system will go from a maximum value when the particle is at the bottom of the potential to a zero when the particle is at the top of the potential, right? If it oscillates like that. So you see that with one particle, temperature, whatever is the meaning of temperature for one particle, which of course you have to be very careful, right? Because temperature is only defined in the thermodynamic limit, of course. But I mean, let's imagine that you do a simulation with a single particle, an harmonic oscillator. You immediately see that the value, at least of the kinetic energy, let's not even call it temperature, oscillates between zero and the maximum value forever, right? So in some sense, the fluctuation of this temperature is of the same order as the average value, which is half of it. Okay, so you see the fluctuation is essentially equal to the instantaneous value of to the average value of the temperature for one particle. If your system is composed of many particles, these fluctuations will reduce, and in the thermodynamic limit, you will essentially have a constant temperature for the average and also for the instantaneous temperature. But it's case like 1 over square root of the number of particles in your system. Okay, let me give you another example of observable that you may wish to calculate. I'm not sure whether this will be considered in the tutorial, but it's actually a very common exercise especially when you study liquids. And this is the so-called pair correlation function. So you look at if you have a system of particles. I'm mentioning this because this is an extremely common type of observable. You have a liquid. Let me say you have a liquid, and well, you sit on a given particle now. You sit on this particle, for example, and you look at all the distances that you have between this particle and all the other particles, right? Like this. And you construct a probability distribution that at the given distance r from a given particle, okay, from this, you have another particle. Okay, so you just look around yourself and you essentially, you do it actually through an histogram in practice. But if you average over several steps, what you will obtain is something typically of the type of this type. Okay, and this is quite universal. I'm showing this because this is a rather universal behavior for essentially all systems. What this is showing is that for example, there is essentially zero probability that two particles come in contact, right? Well, if in contact, you mean really coming in contact at zero distance, right? You have always repulsion at some point between two particles. You also have always a maximum probability for particles to be at a given distance, right? This distance is normally the distance that particles take in the solid, nearest neighbors in the solid, right? In the liquid, there is always a reminiscence of the fact that you have a shell, that you have some type of bonding, regardless of the system you're studying. And so you always have a maximum of the probability at a distance which is, you know, of the order of a few angstroms, which is the typical distance of two particles when they approach each other. And then you have fluctuations which eventually tend to a constant. The constant, of course, comes from the fact that if you're in the disordered system, if you look sufficiently far away from yourself, you're essentially going to see an average distribution which corresponds to the density of your system. So you won't be able to recognize fluctuations, systematic fluctuations, due to the fact that there is a memory of yourself in that particular position. Okay, so this distribution normally tends to a constant, to 1, to the density of your system. Okay, so this is called pair correlation function, and it's one of the most popular pair correlation function. Takes also other names. Okay, it's called GeoBat. Now I don't know how we're doing with time, so it's 9:15. Maybe I think it's probably, I mean, I don't like to talk for 1 hour and a half. So is it okay if we take say 5-minute break? So you can go to the toilet if you need, you can get a glass of water or whatever. So can I suggest that we stop here briefly for 5 minutes and we reconvene in 5 minutes, which for me is 9:30. Let's do 9:35. Okay.
Yeah, fine. Okay.
Sorry, not 9:30.
Yeah, it's fine. Why not? Yeah.
9:35. Okay.
Yes.
Good. Okay. So I'll. What do I do? I'll write it here. We reconvene at 9:35 a.m. Of course, Central European time. So in 5 minutes, approximately 6 minutes.
Central European summertime.
Okay, whatever. It's GMT +2. Okay, see you in a moment. Okay, I think we should start now. Can I start?
Yeah, sure.
Okay, good. So first, I guess there was a question on the chat about the difference between Nosé and Nosé-Hoover. I've been using the word Nosé just because of historical reasons. Nosé was the one who actually came up with the proof that the thermostat samples the canonical ensemble. But in fact, the scheme as I presented is actually called now as Nosé-Hoover. Hoover gave some important contributions in the definition of the algorithm. So in fact, there are several different flavors of these thermostats. I've only shown this qualitative, very sort of poor-man description of the thermostat. But you're right, it's called actually in practice, it's called Nosé-Hoover. Okay, so this is the second part now of my lecture, and this is now going to focus on the potential, right? We are in ab initio community, or a place where a community that wants to learn how to use ab initio methods. So this is the place where ab initio comes into play now. Let me just give you a brief historical, excursus of how the field of potentials, force fields, interatomic potentials, was developed over the years. At the beginning, molecular dynamics was essentially just done what we call classical molecular dynamics. That is, it was the first calculations were done with interatomic potentials, which were written as sum of pair interactions in the 60s at least, and then in the 70s, people started to introduce some environmental variables into the definition of the potential. It was only in the 90s, I would say, with the breakthrough made by Karen Farinello, that the people have started to use the ab initio potential, concretely in molecular dynamics. And it's the last 20 years have been something that, in fact, slightly goes back to the beginning, in the sense that the people are now constructing interatomic potentials based on the ab initio data in what we call ab initio based molecular dynamics. But let me just briefly go back to the beginnings, because this is very instructive also from a number of points of view. So what is the concept? The concept is that suppose you don't know anything about the potential. Well, the first thing that comes to your mind is to say that the energy of interaction between two particles, well, to first approximation, perhaps it can be written as a sum of pair interactions. That is, atom I interacts with atom J with a given potential. In fact, if I can now stop sharing and I'll go back to my, if you take any pair of atom, okay, any pair of atom in the periodic table, and you look at the energy of interaction between two atoms, well, it's quite, one can come up with a quite universal description of this interaction, which certainly has, a repulsive wall at short distances, right? Atoms, any pair of atoms beyond the given distance, they will start to repel each other for a number of reasons, right? Power repulsion, nuclear, repulsion, and so on and so forth. So there is always a steep repulsion wall at very short distances, much shorter than chemical bonds, for example. Then at long distances, we also know that at least neutral systems, they all, that's actually an exact statement, and two neutral systems, they always attract with something that goes like 1 over d to the 6th, right? This is the famous van der Waals coefficient. In fact, it's the long distance interaction between any pair of neutral objects. It goes like this, like -1 over d to the 6th. So these are quite universal statements, right? Any pair of atoms would do that. Now, if you just join these lines analytically, you realize that there will be a point where there is an equilibrium, right, at some distance. And of course, this corresponds to a given energy of equilibrium between any pair of particles. So again, this is any pair of particles, any pair of atoms in the periodic table, with probably 1 or 2 exceptions. Okay, where the differences come into play is when, of course, if you choose different atoms, is what is the distance and what is the depth of this well. I'm sure you're familiar with the fact that covalent bonds, atoms that interact with a covalent bond, like carbon, for example, the distance is very short. Okay, the distance in carbon is about 1 point something angstroms, and the depth of this energy is also quite large. It's of the order of electron volts in the case of chemical bonds, right? So this universal curve has, it's short and it's very deep in the case of covalent interactions. But take helium, for example, right? Take 2 helium atoms, their interaction is extremely weak. So the depth of this potential is less than millivolts, and in fact, even less depending on the rare gases. And the average equilibrium distance can be several angstroms, 10, 20, 50 angstroms, the equilibrium distance between 2 pair of completely neutral and I mean, like rare gases. So while this universal curve in shape qualitatively is the same, the actual quantitative aspects of this can be quite different across different atoms in the periodic table. So let me go back now to my slide here. So if I assume that the 2 particles in my system interact with a pair potential, I write the sum of the energy, I mean the total energy as a sum of pair interactions, making sure I don't count interaction twice. And then, of course, the next step, if I want to improve this potential, is to say, well, how is the interaction between I and J affected by the presence of atom K, for example, right? Clearly, if I take atom K in this figure here, and I move K, say, from the position you see it now, to the position that is exactly in the center between the connecting line between I and J, you will immediately realize that the interaction between I and J is going to be affected. Suppose it was a covalent bond, for example, between I and J. If I place an atom in the middle of a covalent bond, of course, the interaction between I and J is going to be affected. So you clearly see that the pair interaction approximation is really an approximation. And in principle, you need to correct it for the presence of third atom. So this is what scientists did in the 70s. They started to construct potentials that were essentially correcting the pair interactions by including 3 body terms that were supposed to correct the pair interactions for the effect of a third atom, K in this particular case, depending on the position, of course, of atom K with respect to atom I and J. Well, you immediately realize that that's a never-ending story, right? Because even if you now correct it with the presence of of a third atom, you can say, well, but the interaction between I, K, and J is going to be affected by atom whatever, L, right? So there's going to be a 4th atom, which is going to affect, depending on where the 4th atom is, the interaction between I, K, and J. So you must, in principle, include also a term that corrects the 3rd order contribution with the 4th order contribution, 4 bodies, 5 bodies, 6 bodies. In fact, one thing, it has been shown that this is not even, in some cases, it's not even converging as a sum of, as an expansion. Okay, so people have come up with quite different approaches in the later on, especially in the 80s, and especially people have introduced terms that somehow consider the fact that the atom, when two atoms interact, you have to consider in an average way the position of all the other atoms. This is the underlying concept underlying the embedded atom models. You're embedding your pair interactions into something, into an average field, which is the contribution, which essentially gives the contribution of all the other particles to the two-body interaction between these two specific atoms. I don't want to go into any detail about this. I mean, there's plenty of literature about how people have constructed empirical potentials for that. And of course, you have several parameters that you need to fix in deriving your empirical potential. And historically, this was done, especially in the 70s and 80s, by fixing those parameters to experimental values, such as, for example, melting temperatures, equilibrium lattice spacings, dynamical properties, and so on and so forth. But let me now come to the ab initio potential, and let me actually stop sharing this because I need to leave the blackboard now. So the breakthrough came when I wouldn't say people realized, because that was obvious to everybody, but when people started to become, when it started to become possible to say that the potential could be evaluated entirely ab initio instead of right. So what we want to do in our molecular dynamics, as let me remind you, is that we want to solve Newton's equations, and we want to calculate the force. But we know that the force is essentially the derivative with respect to the coordinate of a particle of some sort of energy, which is not only a function of Ri, of course, but it's a function of all the particles in my system. Oops, sorry. I need to do this. R1, R2, blah, 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 blah. Ri, the particle I'm interested in, and Rn, the final. I mean, if I have n particles in my system. Okay, this is a very important concept. Okay, so the energy of my system is, of course, a function of the position of all the particles in my system. If I move one, the total energy will change, right? And when I calculate the force, I need to calculate the derivative with respect to one of these variables. And this will give me the force acting on the on I. As I've seen before, as you've seen before, historically, people have described this as a sum of pair interactions or some embedded scheme or so on and so forth. But the truth is that if one was able to evaluate this total energy of the system for a given configuration of the atoms, ab initio, that will be the solution to the problem. And in fact, this is what we do when we do ab initio molecular dynamics. We're actually calculating the total energy of the system. We're evaluating the force, as you did in, I think, last week. And then we use the force that was calculated with ab initio approximation, with ab initio accuracy, to evolve the molecular dynamics of my system. Okay. Now, let me somehow elaborate a little bit on the complexity of this task, right? So I have my box here, and I have my particles here. Now I'm not going to call them atoms any longer, okay? I'm going to call them ions or nuclei, because in an ab initio framework, the electrons are everywhere, right? I have the particles here. So this is, for example, a nucleus with charge Zi and mass Mi, okay, and position Ri, of course. So the points will be defined by, will be our, what we used to call atomic positions, okay? But then inside this box, I have electrons everywhere, right? Well, let me, just to be a little bit more, let me assume that electrons are somehow localized close to the atoms, for example, okay? So these are electronic distributions. This could be, for example, a typical electronic distribution in a system of particles where the particles are placed, the nuclei are placed in these positions. Okay. So in order to calculate this energy here, I need to solve my quantum mechanical problem for a given configuration of the atoms. So this, of course, means that every time I solve my my quantum mechanical problem, I have to find what is essentially the wave function of the electrons. So this is now the electronic wave function, and it's the ground state wave function. And this is going to be a function of all the electronic coordinates, or only one if we are in density functional theory. If you think in the many-body framework, this is actually the collection of all the position of the electrons. And notice that I'm using now small letters to describe positions of electrons, okay? I'll be consistently using, as I said, capital letters for ions, atoms, or nuclei, and small letters for electrons, okay? So, for example, if I'm describing this particular wave function, the orange wave function inside this inside this simulation box, I will describe it with, well, let me use a collective index for all the electronic particles. But then I have to remember that this is parametrically dependent also on all the Ri positions, right? Because this wave function will be different depending on where the positions of the nuclei are. Okay, so it's a wave function expressed in terms of, as a function in terms of the electronic positions, 1 or n, depending on whether a many body or mean field, but also parametrically on the position of the nuclei. What do I mean by that? What I mean by that is if I change the configuration of the nuclei, I displace them, this will be different. And of course, the wave function will be different because for every given configuration of the nuclei, I will obtain a different wave function. And what I know, of course, is that this wave function is the solution of the Hamiltonian problem. And the Hamiltonian is, of course, a parametric function of the coordinates. Okay, so this wave function will be the ground state, well, let me put the ground state here just to be clear, of the Hamiltonian problem. And the Hamiltonian, of course, is defined for a given configuration of the nuclei, because it depends on where the nuclei are. I mean, the Coulomb potential or the pseudo potential will be placed at the position of the nuclei. So this Hamiltonian depends parametrically on the position of the nuclei. Its ground state for the electrons will be given by the solution of this equation. Okay, so as a consequence, the ground state will depend parametrically on the position of the nuclei. Okay, I hope this is clear, right? So I'm solving the quantum mechanics of the electrons, the ab initio problem, and I'm solving the quantum mechanics of the electron parametrically, that is by changing every time the parameters in this Hamiltonian, which is where the atoms are. Let me actually show it to you a bit more with real equations so that you can, here you go, okay? So this is essentially what I just explained. The box at the bottom right of this slide gives you the parametric Hamiltonian, which depends parametrically on the position of the nuclei. And the energy, the total energy of the system, is the ground state energy of the electronic problem for a given choice of the nuclear position. Now, when I now do ab initio molecular dynamics, what I have to remember is that every time I solve this problem, I need to solve it once. I will have to calculate forces, and I'm normally using Hellman-Feynman theorem to calculate forces. I don't need to go through Hellman-Feynman theorem, I guess. I think you already saw that last week. So there are ways, efficient ways to calculate from the electronic ground state its derivatives with respect to the coordinates. And then I need to evolve. I remember what we discussed at the beginning of the lecture. I need to involve my particles, right? So the next step, so if I now do a one molecular dynamic step, the nuclei will change a little bit, right? Will be displaced. This one will go here. This one will go here. This one will go here. So there will be small displacements, where small depends, of course, on delta t. Delta t I chose, but it will be slightly displaced. Now, the next step of the molecular dynamics, I need to solve again the electronic problem, right? I need to go back here, change the Hamiltonian, find the ground state again. determine the ground state energy, and recalculate the force. Okay, so I hope you get a flavor of the why doing ab initio molecular dynamics is so complex and so time consuming, because every time in principle you move the particles, you have to solve the electronic problem again. You have to find the ground state again of your system. Ground state energy, determine the forces, and then evolve delta T, delta T, delta T, delta T. Okay, so you easily imagine that the complexity of this task is much, much higher than, for example, determining the forces based on a pair potential, right? The pair potential in nanoseconds, with any computer, you can calculate it for an arbitrarily large number of particles. Here, of course, if your system has, I don't know, 1,000 atoms, you're simulating a system of 1,000 atoms. That means calculating the ground state energy and forces of in a simulation box of 1,000 atoms, right? So this may take actually quite a long time. So this is why ab initio molecular dynamics, of course, is limited, much more limited than classical molecular dynamics in terms of sizes of the systems and length of the simulations. Instead of doing, as I said at the beginning, micro, even milliseconds in the case of classical molecular dynamics, with ab initio molecular dynamics, you rarely go above 1 nanosecond of total dynamics. In fact, most simulations are of the order of 10 to 100 picoseconds in terms of total duration of the molecular dynamics. And even in terms of sizes, you rarely go above 1,000 particles in your ab initio simulation, because that's, it has to become quite consuming, time consuming and resources consuming in practice. Okay. Now, having said this, however, I'm sure you're already seeing that we can take advantage of some, some facts here. I said at the beginning, I said a minute ago that you need, every time you evolve the particles, you need to recalculate the ground state of your system. Yeah, that's right. But if your particles move only very little, that is, if this distance is small, and it is small because we are evolving the particles with the small delta T in a continuous dynamics, then of course the solution of this problem is going to be enormously simplified by the fact that I already know the solution of the problem at the previous step, right? In fact, as a guess, the wave function of the system, the entire system at the previous step, is an excellent starting point for the solution of the ground state problem at the next step. It's much better than starting from random orbitals or even some educated guess of what could be the ground state. Okay, so ab initio molecular dynamics takes a lot of advantage from the fact that you already know the solution of the previous step. And so when you evolve it, you can take advantage of that solution. Okay, to speed up, and there are various algorithms that allow you to do that in an efficient way. Let me rephrase this problem in a slightly different sort of mathematical framework, because this is very useful to now understand what is Carparinello molecular dynamics. Okay, so let me, oops. Okay, what much time I have? Yes, a few minutes, almost done. Okay, let me now show you this. This is now the energy of my system, the ground state energy of my system, as a function of the energy of my system as expressed as psi h of r psi as a function of psi. So what am I doing here? I'm fixing Ri, I'm fixing the configuration, and I'm simply, imagining what's happening to the energy, that is to the expectation value of the Hamiltonian, if I vary the wave function. Okay, so I'm here in the realm of quantum mechanics, if you wish. There will be a ground state, okay, and this expectation value, we know already that it has some sort of minimum here, right? I mean, that's the variational principle of quantum mechanics. If I evaluate the energy as an expectation value of the Hamiltonian on an arbitrary wave function, this energy will always have to be variationally higher than the value I obtained for the energy at the ground state, okay? So this is my ground state. And I mean, this is just very qualitative description of what, mind you, I'm using only one coordinate, but this is a Hilbert space, right? Because the wave functions are a Hilbert space. So you have to imagine this as an infinite dimensions not just as one. I'm just collapsing the wave function as if it was a one-dimensional object, right? But it's an Hilbert space. So, but there is a minimum, right? At the corresponding to the ground state in quantum mechanics, if you fix the Hamiltonian, and now I'm fixing the Hamiltonian, this corresponds to a minimum. And of course, I mean, I'm just rephrasing concepts that perhaps are very obvious to you, right? That quantum mechanics finding the ground state is equivalent in a variational picture to identifying the minimum of this object in the space, in the Hilbert space of wave functions. And this is the ground state. Of course, a ground state which will be determined by whatever is the Hamiltonian I've been using here. I'm using the Hamiltonian for a given value of the nuclear positions. And of course, there are several ways to find the minimum of a quantum mechanic. I mean, variationally, I can do diagonalization in a different framework, but I can think of sort of seeing this as an optimization problem, as a minimization problem, in which, for example, if I start from a guess of the wave function here, let me assume that the goal now is to find the ground state. I can start from a guess, a wave function, which is a guess here. And I can try to identify where the minimum is. What do I do? Well, I need to know the derivative of this, right? If I want to determine where I need to move. But the derivative of this with respect to psi, that is the derivative of the, this is just quantum mechanics. It's, of course, it's a functional derivative, right? So this is, forget about the factors, right? I'm really using, you know, Hans waving arguments. Is H psi? Right, the variational, the functional derivative of this object with respect to psi is H psi. Now it depends on, I mean, forget about the details, but essentially, qualitatively, you can say that the force, right? This is the force in principle. I mean, if you see it from a classical point of view, the derivative of your energy with respect to the variable you want to optimize, which is the wave function, is H psi, which is this force acting. Let me use force, but it's not really a force because we're in the quantum space now. We are seeing the quantum problem as a classical problem here, right? Optimization problem. We have a force which pushes the electrons towards the ground state in this direction. And I can come up with many algorithms. Once I know the force, I know the gradient. I can use conjugate gradients. I can use steepest descent, for example. Let me just be very stupid and say that I want to find the minimum of this. Well, then I need to evolve my wave function from the guess following the gradient. Sorry, this is minus the gradient, right? The gradient goes up. This is minus the gradient. Okay, the one that pushes me towards the minimum, of course, I have to go against. Sorry. Yes, yeah, it's so the force is minus the gradient. So if I imagine an algorithm which evolves with time, now it's a fictitious time because I'm just finding the ground state of a quantum problem, and I'm introducing some sort of fictitious, an algorithm time, which says my velocity of this particle, this object that I'm optimizing, goes with the force acting on it, right? This is called steepest descent. It's one of the most stupid and simplest algorithms that you can think about in order if you want to minimize finding the minimum of an object with respect to a variable. And then, you know, in several steps, if you do discretization, you will eventually find the minimum following this gradient. Now, this is, of course, there are much more clever ways to optimize, to find the minimum of a quantum problem. You can diagonalize, you can do Lanczos, you can do conjugate gradients. I mean, quantum espresso has several ways to actually find the minimum. I'm here showing something which is extremely stupid, but it's going to be very useful to understand now Carparinello because of the following. Let me actually make a small digression, which sounds a little bit stupid and silly, but it's the following. Suppose I now do, instead of doing this, I do this. again, let me remind you that we are not in the classical space here. We are working with Hilbert spaces, okay? So I'm just imagining some infinitely dimensional field that evolves with this second order equation following what I call the force, which is the gradient of a potential along this least trajectory. If I do this, what will I obtain? Well, something a little bit different, right? Because this is now second order dynamics in an algorithm time. And so my particle or wave function, depending on how I want to call it, will start, well, it will start oscillating back and forth from here, boom, 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 right? So imagine this in a quantum space, right? This is the ground state. I'm just letting my wave function evolve around the minimum in this infinitely dimension Hilbert space. Okay, this is what I would get. Sounds silly, right? It sounds quite silly. Why should I do that? Why would I like to do that? Well, there is one reason I may want to do that. It's that on average, if you think about it, if I evolve the wave function in this, on average, the wave function will be very close to the ground state on average. It will be oscillating, but on average, it will be very close to the ground state. So if I do this and I evaluate the average value of the wave function, that's not going to be very far from the actual ground state. Okay, we are ready now to move to Carparinello, and Carparinello can easily be understood if I now add the third dimension, which is now the position of the particles, Ri. Once again, I'm collapsing everything into a single dimension, but it's a 3n dimensional space, right? That of the coordinates. In which sense? In the sense that once I found the ground state, and now remember our problem. Our problem is to evolve the wave function, finding the ground state every time we move the atoms. Okay. If I now introduce the variable, the nuclear coordinates, the atomic coordinates, once I find the ground state, I need to now move the particles, right? So I will now be sitting at the position which is slightly displaced in Ri, right? I will have to move in this out of the blackboard in a different space. Everything will change. This will change. The Hamiltonian will change. So I will have to find another minimum, right? So, well, let me now move it a little bit here. So this will be a slightly different parabola. It will be slightly displaced with respect to the original position. Its minimum will also be slightly different with respect to the original minimum, right? Will be somewhere here, for example. Now I draw it a little bit different, but in other words, this reflects a bit more what I said before. If I now want to minimize the wave function for a slightly different choice of the nuclear coordinates, I need to, the ground state will be slightly different, but the original ground state, which was this one here, and now projected this one, will not be very far from the new ground state, which is this one here. So as you can see, I can see the problem of finding the minimum of the quantum problem when the particles evolve in their positions as a problem of identifying the minimum of something which looks like a parabola, which actually moves with time according to the position of the particles. So it's a bit like, having a particle of which you find the minimum here, or perhaps in a ball, for example, and then you move the ball and the ball changes a little bit, the minimum changes, the position of the minimum changes, and you want to continue to keep your ball, your little particle at the bottom of this cup. So Carparinello comes into play when you say that you're actually evolving this, and this is now the magic of Carparinello. Carparinello said, well, why don't we do this simultaneously? Why don't we evolve the Newton's equations for the particles and these fictitious, very strange equations for the electrons simultaneously? In other words, why do we need to find every time we move this parabola, always the ground state? Well, let's stay actually out of it and let's start to oscillate around the minimum, okay? While this parabola moves in space according to the evolution of the nuclear coordinates. So this is essentially the basic principle of Carparinello. Instead of looking every time for the minimum, which is very time consuming, because if you want to look for a minimum every time, every time you fix the value of the nuclear coordinates, you must find a minimum. So you have to solve a quantum mechanical minimization. Here instead, every step, you don't find a minimum. You just do h times psi. It's a simple matrix times vector operation. You don't have to diagonalize h. You don't have to find a minimum eigenvalue. You just do h times psi, which is numerically extremely faster than finding the ground state every time. Now, if you do this, you know, if you let these oscillations here be fast enough, okay, the particle will adiabatically follow the minimum of your parabola. But this has to be fast enough to follow adiabatically the minimum of your parabola. Okay, let me now just summarize it here. Time is almost over. So let me see. No, sorry, this is Feynman. I skipped that. Sorry. Here you go, and here you go. And now I'm essentially summarizing what I just said here at the blackboard. Okay, perhaps a little bit better from a graphical point of view, right? I'm evolving the electrons with this fictitious second order dynamics, which keeps them, and you see now the blue line, this is the Carparinello evolution, closed but never actually in the instantaneous ground state of the particles. The red line instead is the so-called Born-Oppenheimer molecular dynamics. Okay, the molecular dynamics where every time you move the particles, you end up in the you find the ground state of your system. Now, very briefly, can you tell the differences? Yes, there are some differences. And here, for example, on the right side, you see on the left side, you see the forces on the atoms calculated with the electrons in the ground state and the forces calculated with the Carparinello approximation. They are not exactly the same, of course, because your wave function is not exactly the minimum. But what you can see on the right side is that the difference is actually an oscillating function. So on average, the force on the particles is quite similar to the force. And you can make this as small as you want if you, say, make the dynamics of the electrons fast enough. Okay? I think I will just stop here. Oh, sorry. Yes. I'll leave you with some basic text about molecular dynamics, a little bit about the history, the basic papers, and also a very nice and comprehensive book that was written by Dominic Marks and Jörg Hütter about ab initio molecular dynamics, where you'll find essentially everything you want to know. It's a bit old, but it contains really everything you need to know to run ab initio molecular dynamics. And with this, I will stop here, and I'm not sure how it works here.
Thank you very much. Thanks, Sandro. It works that normally we leave the people from Zoom to raise their hand and make questions directly if they want. Meanwhile, I can post to you on the chat some question from the streaming, like one that is here now.
Approach of molecular dynamics to study a system in phase transition water. Okay. All right. This is a very complicated question. I mean, now studying phase transitions, unfortunately, requires a huge effort in terms of statistical sampling, because you have to determine essentially the free energy of different phases, and determining free energies is not straightforward. It requires a lot of statistical sampling. So this can be normally, hardly done with ab initio molecular dynamics. So if your problem is to study specifically a given phase transition, then I would probably do ab initio molecular dynamics. But if your goal is to study, say, an entire phase diagram, including liquids, my suggestion would be to instead use, classical potentials. And I didn't discuss it, of course. I just gave you a flavor at the very beginning. But you can now optimize classical potential based on the ab initio data. And you can do it also now with, machine learning techniques. There are now a plethora of potentials being developed based on ab initio data and say, machine learning, neural networks and so on and so forth. So my suggestion would be, if you need a lot of statistical sampling, to do it with potentials that are optimized based on the ab initio trajectories and ab initio data.
Okay, there is another question from Slack that I can forward you here on Zoom. There you go.
Okay, I want to do molecular dynamic calculation. What do you put on the table for consideration? Oops, scrolling too fast. Oh, the question is the CPMD versus Born-Oppenheimer. Yes, that's a very good question. So it has to do with your, essentially, just as a summary, it's a long discussion, but I can summarize it as follows. For insulators, it turns out that normally Carpanella molecular dynamics works better than Born-Oppenheimer molecular dynamics. For metals or for systems with small gaps, small electronic gaps, it's the opposite. You better do Born-Oppenheimer molecular dynamics. It essentially has to do with the curvature of this parabola that I was showing at the end of my lecture. For an insulator, that the curvature of that parabola is very high. So the parabola is very steep. And so it's easy to follow. The electrons have an easy job in following adiabatically the evolution of the nuclei. For metals, the parabola is very flat, because actually the curvature of that parabola is the square root of the energy gap of your system. It's been shown that. And so for metals, you better use Born-Oppenheimer. It's a bit of a trade-off. It depends also on the efficiency of your code, of course. If you have an extremely efficient code for Born-Oppenheimer molecular dynamics, you better use Born-Oppenheimer molecular dynamics all the way. One more.
There are two more. Yeah, there are two more that I already posted.
Yes. Okay. Can I then I add, if I can, just one last slide which addresses that last question, if I can. Here. Okay. These are all the things I would have loved to tell you, but I didn't have the time to do. So the first question is actually the one that was in the chart that addresses the first one. I'm assuming here that you can do classical molecular dynamics on the nuclei. This is true for 99% of the atoms, but there are exceptions, and helium is a very notable exception. Helium is a quantum fluid, or has extremely important quantum effects. So yeah, you have to be careful. Hydrogen, of course, the lighter is the particle, the less the more you have to be careful about doing quantum dynamics for the particles. And let me just take this opportunity to mention three more topics that for you, to think about. One is how, I've been discussing essentially ground state dynamics, but it's extremely interesting to also look at the dynamics of particles when the electrons are in excited states. Things of photochemistry, for example. I didn't discuss how to accelerate sampling in case you want to jump from different. I just alluded to it when I mentioned the ergodic theorem. I'm mentioning these things because they're all extremely fast expanding areas of research. So you might be interested in somehow looking at what's happening in these areas. And then only at the end, I mentioned this concept of now building using machine learning, building classical potentials, that is interatomic potentials, the way we used to do it in the 60s and 70s, but with parameters that are now determined based on ab initio data.
Okay, there are two, I think, one from the streaming and one from the Slack, and then we can close. So one is how to do melt quenching, and the other one is I posted it on Zoom if you want to answer.
Where is it? Sorry. Where the first one is what? Sorry, I didn't understand the question.
Is this one here?
How to do melt quenching? I'm not sure what. I guess this refers to the to how we produce amorphous systems. We normally produce them in simulations, at least, but also in the real life by quenching melts. And there's, I think, the big question here is how to somehow approach the timescales that are required to produce correctly an amorphous system. Ordinary glass is a typical example system that is obtained by slow, even on real-time scales dynamics. It takes minutes, if not seconds. I mean, I was born in Venice, so I know very well how to produce arts masterpieces with glass. And it takes minutes, in fact, even hours to obtain the final product. So this is clearly outside of reach for molecular dynamics, as a matter of fact, not to mention ab initio molecular dynamics. So there are techniques that one can use to speed up the quenching of melts to obtain amorphous systems. Yes.
Okay. I think it's we can take the last question from the Slack channel. Is it possible to perform molecular dynamics by using implicit method, which the solution can converge at any values of time step?
Sorry, say it again. Is it possible?
I can post it here so you can read.
Yes, please.
Yeah, go ahead.
By using implicit method, which solution can converge at any values of time step. I think this is what we call Born-Oppenheimer molecular dynamics. So every step we find the ground state of the electronic wave function. I guess, I mean, the issue here is to which precision you want to obtain the ground state of your function, because of course, I mean, numerically, you will never get exactly the ground state. And that difference can be important. In fact, one of the main problems of Born-Oppenheimer molecular dynamics is the fact that your solution, the error you're making in determining the ground state is normally biased in a given direction in wave function space. And that introduces a systematic error in the determination of the ground state, in the determination of the ground state energy. Something that the Campanello method doesn't have, because the Campanello method has the wave function oscillating back and forth. So you're sort of, averaging out all possible errors you're making because of the fact that you're not exactly in the ground state.
Okay, great. I think we can close it here. I would like to quote a comment from the streaming saying, a great lecture, Professor Scandolo, very clear and captivating. Really like the interactive aspect of the lecture. So thanks a lot. I think we reconvene at 10:35 with the Enson session.
And thank you.